Okay, welcome to Chapter 10. We're going to talk about functions. This is a brand new concept. You would not have seen function notation and the idea of using functions in beginning algebra. So here we are. So first off, what are our goals? Our goal is to answer the question, what is a function? Then we're going to graphically look at functions, and we're going to find the domain and the range using the vertical line test. Then we're going to algebraically find the domain and range, and also, looking at a function, determine if it is a function. And last but not least, we're going to talk about how odd function notation looks, how much it looks like other things. So the first part of this, of course, is what is a function? So simply, a function is a rule that makes input into output. But there's a caveat where there is only one output for each input. So we're going to talk about that first geometrically, and then we're going to look at that algebraically. Now, what are we talking about when we say input into output? So there's a lot of ways of talking about the input and the output of a function. So the input could be called x, so I'm looking at that column. It could be called the independent variable. If you write it as an ordered pair, it's the first component. And here's another word that may be new, and that is domain. So x is in the domain. Now the output, looking to the right of our rule, that function machine there, could be called y. It's the dependent variable. It depends on what you put in. The second component of the ordered pair, or another new range, another new word, in the range. Now notice that x, y is in alphabetic order, and the d in domain and the r in range are in alphabetic order. So our second goal is to use the vertical line test to determine whether we have a function. So here's a graph. It's a sideways parabola. It's actually x equals y squared, and it is not a function. And you can see that because the input of 2 has two outputs, 1 and -1. Now, geometrically, that means that any time a vertical line crosses a curve or a line twice, it is not a function. And I should say more than once when I say twice. The domain, remember, is all possible inputs, and the range is all possible outputs. Okay, so on this page we're going to use the graphs of relations to decide whether they're functions. So we're going to ask the question, is it a function? What's its domain? And what's its range? Now this first example, when you take a look at this, you notice that it has two outputs for the same input. In other words, when x equals 1, there's two y values with those two dots there for outputs. So this is not a function. So our first answer is no, it's not a function. Now for the domain and the range, we're going to ask what the set of permissible values is. For the domain, that's the set of permissible x values. So that means we're looking at this curve and we're asking what x values it can take on. And what we notice immediately is that it can take on x values no smaller than -1 and as large as it likes. That curve continues both the top branch and the lower branch to infinity. So from -1 to infinity. And that's exactly how we're going to show this, as an interval. Now notice that there's a bracket at -1. That means that the -1 is included in the domain. Now we never put brackets on infinities because you can't actually get to them. In many senses, they're a limiting concept, not a number. So -1 with a bracket to say that we're including it, to infinity with a parenthesis to say that we're not. Now, one of the things that's important about looking at graphs and determining whether they're functions and what the domain and the range is that it teaches you how to interpret graphs. So for example, when we take a look at the end, what looks like the end of this sideways parabola, at both of these ends here, we have to learn to see that it is clearly going to the right. Definitely going to the right, perhaps going to the right more than anything else. But it's also going, in the first case, up, and in the second case, down. That is, it's getting larger at the top, and it's getting smaller at the bottom. Now it'll continue to do that. So the range is actually everything, negative infinity to positive infinity. Now you can write that, or you can write a capital R that's kind of bold, but because bold R's just look like bold capital R's, there's actually special notation for this, and that's an R with 2 vertical bars. Now, taking a look at this second graph, the first thing that you might be concerned about is what's going on near the origin, near the point 0, 0. And that is a concern. So remember, what we're doing with these is we're learning how to interpret these graphs. So when you take a look at this, what you're asked to see is that as this curve goes from left to right, in other words, as it's increasing in the third quadrant towards the origin there, you're invited to see that it is getting steeper and steeper and steeper and steeper. And it almost looks vertical. It looks like it kind of merges with the y-axis for a little bit in there. But what you're invited to believe is that it is only infinitely steep at one point, and that is at the origin. And on the approach to it and then leaving it, it's not infinitely steep, which means that a vertical line, as a vertical line sweeps across this curve, it only crosses the curve once. So this is in fact a function. So we would say, yes, this is a function. Now hopefully you can see when it comes to the domain that we can go as far to the right as we wish, past 2. We can go as far to the left as we wish. That this curve continues, this function continues, infinitely in both directions. Remember, our set of permissible x values is our domain, so that's everything. We can go as far to the left as we like, as far to the right as we like. Now this curve is increasing as it's going to the right. Not terribly so, but it's definitely increasing. And as it's going to the left, it's decreasing. Not as steeply as it's going to the right or the left, but it is going up and down, which means that that range is also all real numbers, negative infinity to positive infinity, or that special capital R. Now, this oval that we're looking at next clearly is not a function. And we can see that dashed line showing us that it intersects the oval twice. For example, for whatever that input is on the x-axis, there's 2 points on the y-axis. So this is not a function. So our first answer would be no. Now, the domain is the set of permissible x values. So when we look at the x-axis, we see that it goes from -1 to 1. And so your first response might be that just like that previous curve that only gets to vertical slope once, you might ask the question, well, does it actually get to 1 and -1? And remember, what we're learning here is how to interpret graphs. And so when you look at this, you are invited to believe that this graph means that the oval is actually passing through, that ellipse is actually passing through -1 and is actually passing through +1. So we can see that the domain includes -1 and +1. In fact, it goes from -1 to +1 and includes those two endpoints. Now, similarly, when we look at the y-axis to find the range, we see that it goes up as high as 2 and down as far as -2. So our range is going to be -2 to 2. This next example uses a dashed line in a different way. So I first want to point out that along the y-axis, there's a dashed line here. So look at that closely. Now that's a different dashed line than we used in the previous example to show that that ellipse was not a function. This dashed line is called an asymptote. And what it means is that this curve, as it's going to the left, is definitely getting closer and closer and closer and closer to the x-axis. But that dashed line tells us that it's asymptotic. Now, curves can cross asymptotes, but in Math 120, and unless you're in a different case, it's not going to. That is meant to show that it's getting closer and closer and closer without ever touching it. So imagine folding a piece of paper. You can take a piece of paper and you can fold it in half, and you can fold it in half again, and each time it's getting closer to 0. So you can fold it once and it's now half as much. You can fold it twice and it's now a quarter as much. An eighth, a 16th, 32nd, you get the idea. It's getting closer and closer to 0 without ever getting there. This is actually an exponential curve that we're looking at. We're looking at the graph of y equals 2 to the x, where x is an exponent. And this is asking you to see that you'll never ever get to 0. Well, let's answer the questions. Is this a function? Well, I can imagine a vertical line moving across this curve, and I can see that it only ever crosses once. So this is, in fact, a function. Now, the domain is the set of permissible x values, and I hope you can see that this line is going to the right as well as going to the left. So the domain is all real numbers, negative infinity to positive infinity. Now the range, clearly, this curve's going up. So clearly the range goes to infinity. But remember, it does not go to 0. It gets close, but it never gets there. So this is our first example where we have to put parentheses around a number, because we're not actually getting to that 0. Now, there are such things as this next curve. There are curves like this. In fact, the formula is given for you in the side there. There's the equation of this line, or of this curve, sorry, not a line. And notice that it has 2 dashed lines. Those dashed lines are asymptotes. And like the previous example, these are asymptotes that the curve does not cross. So these 2 asymptotes tell us that the curve gets as close as you like to the 2 asymptotes, but never actually gets there. So you can imagine folding a piece of paper, always getting closer and closer to 0, but never actually getting there. So of course our first question is this a function? And our answer to that question has to be yes. So we're going to answer yes to that first question. Now the domain is the set of all permissible x values. So when we look at all permissible x values, we can see that we can go as far to the left as we like, so negative infinity over there, and similarly we can go as far to the right as we like, so positive infinity over there. We simply can't make it to 1. So the only thing that's excluded from our domain, the only value that we have to take out, is 1. Now the way we do that is fairly complicated. There's nicer notation for this, but involves using backslashes and all sorts of other stuff. So we're going to write it like this in our interval notation with that union symbol between them, saying that the domain could be on either side. So take a look at the left side. This curve goes from negative infinity all the way up to 1, and we show that with the interval from negative infinity to 1. Notice there's a parenthesis at 1 saying that we have to stop there. Then we start up again at 1, never actually having gotten to 1, and we keep on going to the right all the way to infinity. So there's our second interval, 1 to infinity. Now, we put a union sign between these because you could be on either side of this. So our interval, or our formed with the union symbol, is negative infinity to 1 or 1 to infinity. All that is to exclude just one value. Those parentheses on 1 say you can get as close as you like on the left, as close as you like on the right, but you cannot get to 1. Now, if you turn your head 90 degrees, you can convince yourself that the range is exactly the same thing, and that is the only value on the y-axis that's excluded is also at 1. We can get as close to 1 as we like from above. We can get as close as we like to 1 from below, but we cannot actually get to 1. This last example is reminding us what these dots mean. So this filled in dot is telling us that that point is included. In other words, the point x equals 2, y equals 1 is on the graph, while the point above it up here at x equals 2, y equals 2 is not included in the graph. So our first question, is this a function? So we ask about a vertical line. So here's a vertical line, and we move it across the function, and we see it's only intersecting once as we go. And then we might ask what happens here at 2, because it looks like it might be taking on two different outputs there. So remind yourself about the dots. I claim that when x equals 2, when our input is 2, our output is 1, nothing else. So at 2, we're still looking at a function. Now you might say, well, what happens immediately to the right of 2? Let's say 2.5 or 3 out here. And if we go out to 3, we now have a point on this upper branch, and there's similarly just one output. So this is in fact a function. So our answer to that first question is yes, we're a function. Now, if I simply look at the set of permissible x values, there's nothing going on here at all. I simply go from the left side of 2 to the right side of 2, and I have an answer for, that is an output for each of those inputs. So the domain, the set of permissible x values, remember they're in alphabetical order. X goes with D and Y goes with R, X, Y, dr. The set of permissible x values, the domain is everything. Now the range is not everything. The range skips over that unit between 1 and 2. So clearly we can get to 1 and we can get to anything below 1. And similarly, we can get to anything above 2. But we have to skip that interval between 1 and 2. And of course, what makes this a little bit more interesting is it's not the whole interval we're skipping, because notice we can actually make it on the y-axis to 1. So our range includes 1. It goes from -infinity to 1, and then it starts again at 2. But it does not include 2. That open dot tells us that it continues from 2 to infinity. Okay, now we're going to look at doing this algebraically. And so the question is, can we look at an equation and determine if it's a function? And for the purposes of this class, we definitely can. We have to check 3 things, and once we've done that, we can say, just by looking at the equation, that we have a function. So first off, it has to be solved for y. So y equals. And that also means, and maybe this is obvious, that y only appears once. It's not a recursive equation. The second thing is we can't have the best way of getting 2 answers out of something. Remember, the quadratic equation gives us the quadratic formula gives us 2 answers to a quadratic equation because of that plus or minus sign. When there are 2 solutions, it'll give it to us because of the plus or minus sign. Now, similarly, for us, it's easy to spot functions. If it's solved for y and y only appears once, there's no plus or minus signs, and there's only elementary functions. In mathematics, elementary is not derogatory in any way. It says it's more like fundamental or essential. So things you've seen like plus and minus and multiplication and division and roots, like here's the nth root, so you can have the 5th root of a 7th root. And something that is new and is something we're going to be talking about in chapter 10 a lot, and that is exponentiation. So notice here that there's a lot going on in that set of symbols. A to the xth power is what you think it is. The variable is the exponent. The base is a constant. So remember how this works. We choose constants or literals from the beginning of the alphabet, and we choose variables from the end of the alphabet. So when I see a to the x, I'm thinking 3 to the x, 2 to the x, pi to the x, e to the x. I'm thinking where the base is a constant. So we use an a to say, well, I don't know what it is, but the base is a constant, a literal, a parameter. Now, when I teach this in pre-algebra, I use a sticky note. I write an A on the sticky note, and I hide a number on the board underneath the sticky note. And I say, hey, you know, there's a number underneath that A. We don't know what it is. It's not changing just because I put a sticky note over it and called it A. The true exponent here is x. So using these three tests, we can look at an equation and determine if it's a function. Now, we also want to be able to determine what can't happen. In other words, what limits the domain. So remind yourself that the domain is the set of all possible inputs, that is, all possible x values. So let's look at some cases. Let's look at radicals and let's look at denominators. Now, here's a word that may be new to you, and that is the stuff inside the radical is called the radicand, and the radicand must be non-negative. So make sure that you see that putting that non in front of the word negative means that it can be anything but a negative, so 0 or a positive. So we can write that in as an equation or as an inequality by saying that the radicand has to be greater than or equal to 0. So this is how we're going to find our domain when we've got not a graph but an equation. So in this first example, we see that y equals the square root of x plus 3, and the radicand is x plus 3. So we say, well, I wonder when x plus 3 is greater than or equal to 0. So we subtract 3 from both sides, and we learn that the radicand is greater than or equal to 0 when x is greater than or equal to negative 3. And that means that we can have x values as small as negative 3, and including negative 3, you can take the square root of 0. So for example, if I had x equals negative 3, I could plug that in, and I'd learn that negative 3 plus 3 is 0. The square root of 0 is 0. So that negative 3 is included. Make sure that you see that those brackets there have meaning. And of course, we can get as large as we like. You can add x to a positive number and get another positive number and take the square root of that. So there we've got our domain for the equation y equals the square root of x plus 3. Denominators cannot be 0. This is a huge issue. There's no way around this. There's actually ways around taking square roots of negatives, and that's complex numbers. But there really is no way around dividing by 0. We leave the world of numbers. That's a more philosophical question than it is a mathematical question. So you can't have a 0 in the denominator. And when we say you cannot have something, we basically say that the denominator cannot be 0. So we strike out that equal sign to say anything but 0. So take a look at our next example, xy equals 3. And your first response may be, well, there is no denominator here. I don't see the problem. But remember that for this to be a function, we have to have y equals. It has to be solved for y, and the y has to appear just once. So the first thing that we have to do with this example is get the y by itself. So we notice that the y is attached to that x by multiplication. X is undone with division. So we're going to divide both sides by x. And the moment we do that, we see that we do in fact have a function, y equals 3 over x. But we also have an issue with the domain, and that is that we cannot divide by 0. So that x down there cannot be 0. So we simply say x cannot be 0. That's how we'd say that in an algebraic setting. To explicitly state the domain, we have to say, well, you can be anything you like, but you can't be 0. So take a look at this notation again. We saw it on the previous page. It says that x could be anything from negative infinity up to 0, so any negative numbers. Notice that that 0 has a parenthesis. That's excluding it from that first interval. Or we're saying that you could start at 0, assuming that you don't include 0, and go all the way to infinity. So that's a way of saying everything but 0. Now let's take these two things together and let's see what we've got. So this last example, notice, has both issues. It has a radical and it has a denominator. So let's look at the radical first. So there's a radical. Radicals, or in this case the square root, cannot be 0. So we cannot divide by 0. So we square both sides, and we add x to both sides, and we learn that x cannot be 3. Now notice that it's not the radical that's preventing x from being 3. It's the denominator that's preventing x from being 3. If you tried to put a 3 in for x here, you'd be talking about 3 minus 3, which is 0. And you're saying, well, that's perfectly fine in terms of the radical, and you're right. But the moment you've taken that square root of 0, you've got a 0 in the denominator. So in this first case, we're saying, hey, that denominator cannot be 0. X cannot be 3. Now, it's also a radical, which means that there's more than just one thing being excluded inside of that radical. We have to remind ourselves that a square root cannot be negative. I should say that the radicand cannot be negative. So we take that radicand and we say you've got to be positive or 0. We add x to both sides, and we learn that 3 is greater than or equal to x. Now, both of these things have to be true. X cannot be 3. We just learned from looking at the denominator. So therefore, when we say x is less than or equal to 3, we have to get rid of that equal part. So written algebraically, 3 is greater than x, and the domain says, well, you can get as big as you like, but you can't exceed 3. So negatives are fine. Now, when you're looking at this, you might say, negatives are fine. How are negatives fine? That doesn't seem reasonable, except for the fact that in the equation, we're changing the sign on x. So negatives are actually becoming positives. So all that infinitely many negative numbers from negative infinity to 0, they're great. Because when we put it in the equation, they change their sign, become a positive. We add 3 to them, and we get something positive inside the radical. The problems happen greater than 3. So imagine something like 4. Well, 3 minus 4 is negative 1, and the radical has no interest in that in terms of the domain. So the last topic here is, what is function notation? What on earth are we doing? We've been talking about what functions are. We've been using functions to find the domain and the range. But what is this function notation? So this is a new topic by any measure. So first off, let me remind you that parentheses are doing a lot for us already. So here's an example. It's a perfectly fine example with one pair of parentheses. So you might say, yeah, that's parentheses. They appear in algebra problems a lot. Now, notice that the first thing that the parentheses are doing here is reminding us of the order of operations. They say to work inside first. So the first thing I might do with this is do the subtraction. 2 minus 5 is negative 3. Notice the parentheses are still there, because now we're saying we've got a base for an exponent. So in the next step, we're going to say, hey, that base is negative 3. Negative 3 squared is 9. And notice the parentheses are still there. The parentheses are still there because parentheses also imply multiplication. And of course, 3 times 9 is 27. So parentheses are doing a lot for us already. But we're going to use parentheses. And this is standard notation. It's used in science. It's used in medicine. Of course, it's used throughout mathematics. Parentheses enclose the argument. Now, the argument is a fancy word of talking about the input of a function, so those x values. So let's break up a function notation. So here's f, that's its name. The name of this function is f. There's an x there, that's the argument, that's the input. And we read this in an extraordinary way. We say f of x is our function. F of x, let's talk about that for a second. Of is exactly how we say multiplication. So if I say, what's half of 6? You're going to tell me 3, because half times 6 equals 3. So of means to multiply. So what have we got? We're using the word of. We're using parentheses. Both of those things look and sound like multiplication. But I'm going to say it again, this is not multiplication. We are not multiplying f times x. In fact, that wouldn't make any sense. A function is a separate thing from an argument. So f of x is our function. So how would I read this statement? I'd read this by saying that f of the input is the output. So when we see those parentheses, we read it as of. Now, why do we have function notation? What are the advantages of function notation? One of the biggest ones is it allows us to have several functions, several different rules, all in the same problem. So an f, a g, an h, a j, a k, an l, all sorts of functions running around all at once. By giving them names, we're not going to be confused. They've all got different names. We can refer to them by their function name. And perhaps equally important is that parenthesis or the parentheses enclosing the argument reminds us what the input is. So we can see the input and what we inputted that value into. So we can see the name of the function and what we put into it all at the same time. So let's take a look at this. Notice we've got two functions running around. We've got a y equals x squared plus 1, and we're accustomed to seeing rules written that way. Might even imagine graphing it. But we're going to rename this function f. So instead of calling it y, we're going to call it f of x equals x squared plus 1. So y has become f of x. In other words, that's going to remind us what we put in, and we're going to name that function f. Here's a second function, y equals 2x minus 3. We're going to rename it g. So now g of x equals 2x minus 3. So let's answer some questions. This first question says, and that is a question, that's a perfectly good way of writing it, f of 5. Well, that means we need to go get the rule called f, and we need to put a 5 in the place of x. So let's see, this rule says to square and then add 1. So if we square 5, we get 25. If we add 1, we get 26. So f of 5 is 26. Now let's think about this for a second. That tells us that if I put 5 into the rule called f, I get a 26 out. Notice that I see three things. I see the input, what I put that input into, namely f, and what I got out. F of 5 is 26. The rule called f makes a 5 into a 26. Now this second question asks me, what's g of 3? So it tells me to go find the rule called g and plug a 3 in. Well, the rule called g says that it multiplies by 2 and then subtracts 3. So we're supposed to take a 3, multiply it by 2, that's 6, and then subtract 3, and of course we get a 3 out. So what is that saying? That's saying that g of 3 is 3. So let's go through that again. G of 3 is 3 means that if I put 3 into the rule called g, I get a 3 out. So I see the input, the output, and what rule made the input into the output. Now sometimes the variable itself is called a dummy variable, and this next example is meant to illustrate that. Remember that we've got the rule called f of x, and f of x makes x into x squared plus 1. So you might say, what's f of n? Well, it's in a sense the exact same thing. It makes n into n squared plus 1. So what happens when we substitute an n into our rule? We get n squared plus 1. Now, more important is the idea that we can substitute an expression like n minus 1 into a function like g. So here's the question, what is g of n minus 1? Well, it tells us to go get the rule called g. So here's our function g, and it tells us to substitute in n minus 1. So wherever we see an x in that equation, we're going to substitute in an n minus 1. So here's 2, and then in parentheses n minus 1, because that 2 is being multiplied by x minus 3. Now we can simplify this. We can do the distribution and then combine like terms. So 2 times n times and then 2 times negative 1 gives us 2n n minus 2, and of course we're subtracting 3. Well, we can combine the constant terms, negative 2 and negative 3, and we can get 2n minus 5. So when we've done the little algebraic simplification there, we can say that g of n minus 1 is 2n minus 5. In other words, we can embed in function notation a little algebra. So there's an introduction to the power of functions, how we can spot functions algebraically just by looking at them with our 3 rules, how we can spot a function by looking at its graph, and how we can read graphs. Also, some new words like domain and range, like input and output, and even the word argument when we're looking at function notation. But perhaps most important is in Chapter 10.1 is this extraordinary use of parentheses. They're no longer just grouping symbols and bases for exponents and multiplication symbols. They're now almost transcendent of all of that. They're now parts of rules, allowing us to see what we substituted in and into what. So that concludes 10.1. Hope you enjoyed it.